Welcome back to Visual Civil. In this video, we will study the classification of beams. Beams are classified based on their position with slabs, their support condition, and their reinforcement placement. First, we will explore the types of beam referring to its position with slab. So, begin with the drop beam. This is the most familiar type of beam. It projects below the slab level and is widely used in the residential and commercial structures. Next, we have the inverted beam. Unlike drop beam, this is projecting above the slab level. The inverted beam is generally adopted where a flat ceiling appearance is required, or in sunken slab arrangements such as toilet blocks. Next in this category is the hidden beam. It is also called a concealed beam. It is embedded within the slab thickness, so you won't see it projecting up or down. Hidden beams are used to achieve a flat ceiling look while still transferring the load effectively. So, to recap, drop beams are projecting downwards while inverted beams are projecting upwards. The hidden beams are staying inside the slab, giving a clean ceiling look. Each type serves a unique purpose depending on structural and aesthetic needs. Now, let us move to next category, that is types of beams based on support condition. In this, first type is simply supported beam. This type of beam rests on two supports, usually a pin and a roller support. You will generally find this type of beam as a lintel over opening and bridge decks. Moving on, we have the fixed beam. It is rigidly held at both ends, preventing rotation. This type of beam can be seen in continuous frames of building and industrial shade, etc. The fixed beam reduces the deflection but requires careful detailing of reinforcement at support. Another type is the cantilever beam. A cantilever beam is fixed at one end and free at the other. This type of beam is commonly used in balconies, canopies, and projections where support is only available on one side. The fixed end must be adequately reinforced to resist bending and shear. Finally, in this category, let us discuss about continuous beam. This type of beam extends over more than two supports. It is used in multi-span slab, bridges, and long corridors. They distribute loads very efficiently and reduce bending moment compared to single span beam. Now let us understand another category as singly reinforced and doubly reinforced type beam. Consider a simply supported beam carrying a uniformly distributed load as shown here. When the load acts on the beam, it bends, causing compression in the upper face and tension in the lower face. Concrete is excellent at resisting compression on the top side. However, it is weak in tension and cannot withstand the stresses at the bottom. That is why reinforcing steel bars are placed near the tension zone at the bottom of the beam to resist these forces. Now, let us cut a section at the midpoint of the beam along line XX. In this section, the portion above the neutral axis is in compression while the portion below is in tension. The rebars are positioned in the tension zone here at the bottom. But that's not all. The beam also experiences shear stress, especially near the supports due to shear forces. To resist this, shear reinforcement is provided in the form of stirrups. And to hold these stirrups in place, we need at least two anchor bars in the compression zone, located at the top of the beam. That means, in practice, beams have a minimum of two bars at both the compression and tension faces. Now, based on this discussion, let us try to understand the singly and doubly reinforced beam. By considering section as singly reinforced, the moment of resistance will be calculated using reinforcement in the tension side only and concrete in the compression side, irrespective of two anchor bars in compression zone at top. If this moment of resistance exceeds the applied moment, the design is adequate. But if it is not, then depth is increased and the section is redesigned. But when the depth is restricted due to some practical situations, we need to place additional reinforcement in the compression side to take care of a compressive stresses. In this case, the moment of resistance is calculated using steel in both tension and compression zones along with concrete in compression. This gives rise to doubly reinforced beam. Because reinforcement is present on both tension and compression faces, doubly reinforced beams are especially useful in the situation where reversal of the stresses may occur. Now, let us understand another type, that is flanged beam. In a monolithic beam slab system, the slab portion above the beam acts as a flange while the rectangular portion below acts as a web. This configuration produces the flanged beam. For interior spans of floors, roofs and decks where the slab is available on both sides, the cross section looks like the letter T. That is why it is called as a T-beam. Here, the slab flange adds strength by resisting compression while the web handles the shear and bending. At the edges or last spans of the slab is available only on one side of the beam. This makes the cross section looks like the letter L. Hence, it is called as a L-beam. It works similarly to a T-beam, but it is designed for edge conditions. Now, let us understand the behavior of a flanged beam under the bending. In sagging bending, when the beam curves downward, the slab flange is in compression, which makes the flanged beam stronger. But in hogging bending, when the beam curves upwards, the slab flanges goes into tension. In this case, the beam behaves more like a rectangular beam, and we need to design it accordingly. So, whether it's a T-beam in the interior or an L-beam at the edge, both are clever ways to using the slab and beam together to carry loads more efficiently. That's a wrap on this video. If you found this video helpful, give us thumbs up and don't forget to subscribe for more design insights. Drop your queries or experiences in the comments below and we might feature them in our next video. Until then, keep learning.